Picture. Beautiful. All right. Can minimize. All right. So if I share, I should be sharing this. Cool. All right. So make sure I have everything here. Yeah. Okay, cool. So let's do this right here. Um, so the questions are gonna be kind of like this. The only difference is that the forces will be either a point or distributed. It's just the whole concept, right? So the reactions could be in different places, but it's going to be mostly like this. The goal is to learn how to do the shear diagram and the moment diagram. So I'll give you an example. Um, so they're asking us draw the shear and bending moments. Okay. So I already have all this here to save time. Last time was complicated and not very clear. So the reactions are these, and how you get to them are like so. If you have summation of forces in y, and x is going to be 0, we don't care because this is going to be the only one in x. This one is a roller, so it can move, kind of like a bridge. Um, but this is an actual type of reaction because it will move so that it doesn't crack. So you will just have elasticity on the beams. So x is 0, y is not 0. Y, y direction is not 0, y being up positive. So ay plus cy minus p. This is a general case. A, B, and L could be anything. Um, and so at this point, we should be able to. The beautiful thing here is that applies for any length, any B, any A. So if A equals B, it's just the middle. The math is the same for everything. Just what has to change is obviously if the length is too high, too large, you need the inertial, the internal part of it to be more bulky, or instead of being a one beam, you're gonna have to be like a lot of rods and then concrete. So that's the thing that you learn later when you see mechanics of materials. Right now in statics, you're learning how to determine what the reactions are on the static points, which are A and B. This later on, you'll see that this will deform like this actually. They will have a deformation like this. So this point is not necessarily static, it can have some vibration. But anyway, we're using this point to determine the forces. How do you get to this point? At this, so you have one unknown and two unknowns, or only one equation. Just like before, we do summation of momentum. This is pretty similar to the homework, so I just want to make sure that everybody's on the same page, so we can do more difficult ones. And then positive, I always decide to go for counterclockwise is positive. So anything that I take on my momentum equation is going to be is equal to 0. I keep saying momentum, sorry, it's because I've been working with fluids. My moment. Momentum is for dynamics, moment is for statics. Sorry, I was working on a fluids project before this. Um, so the if you do moment around A, you're gonna have that P is is clockwise, so it's gonna be negative, and C is counterclockwise, so it's gonna be positive. So from Z, not Z as Zulu, but C as Charlie. So from C to A, you're gonna have CY times the length. That should be clear by now. And then minus, because it's going the opposite direction, P times A. We're gonna decide to do the moment there because where you have the most amount of forces A, and because the fixed point. All right, this is equal to 0, so CY times L equals P times A. So in other words, if you rearrange this, you're gonna get that CY is PA divided by L. So we got this. Now, how do you get AY? You just bring this is just algebra here. So AY minus PA over L minus P equal to 0. Then you're gonna see that if you do AY minus, take this like this, or equal, let's do equal, um, P that multiplies, both of them are positive now. And if you do L, BPA minus PL, if you take the P out, is L minus A, because you're taking it to the other side, over L. And L minus A is B. All right, so just do the math by yourself. You'll see that you're gonna get the AY is B and B divided by L. All right, cool. So that's that. So this is something that we already know. They're asking you to draw. This is the thing that we're gonna be focusing on the exam mostly. So you need to get all that so that you can draw the diagrams. All right, so you draw the diagrams like so. Bring the geometry again, and you have a positive force that is PB divided by L, and another one that is PBA divided by L. All right, so it's a point, is a line going up, and then a line going down at B as boy, and then a line going up as C as Charlie. And then you connect them through with straight lines. That's if it's a point force. This is the simplest case. That's why we're starting here. And then the moment is one higher up. So if you have a straight line, you're gonna have a slope. And if it's on the positive side of the equation, it's a plus, a positive slope. If it's on the negative side of the graph, it's a negative slope. So from here to here, you have a slope of PA divided by L. All right. So this is simple as it gets. This is one case that is very common because you have certain forces that like a, like a post or power, things like that could be assumed to be point forces. All right. So let's do something more complicated. This one is great for, if you understand this one, you're definitely gonna get a really good grade on the exam, I think. Um, oh, by the way, before I move on, what was the maximum? The maximum is here. And in order to do the maximum, we have to solve the equations actually. So let's do the maximum. Well, we already used the equation for it. So the only thing you have to do is use the method of section for the maximum. Oops, didn't mean to do that. All right. Wait, there's a way to do a larger circle dot. This is gonna take me forever. Okay. Just gonna go ahead and draw here. So to get the maximum, we're gonna use section here. We're gonna say that V, this force V. Actually, let's do it here so we don't have, so we can use P and. So let's do one here before the P, the force. So this one, this cut here, this V is gonna be the opposite of AY. So VY at section 1 equals negative PAL. So negative PAL. Let me see. Where do we want to do that cut? If we can do PAL or PBL. So let's start from this point better. So we're gonna do from here to here, this whole section. This whole section. So here we have a force V. You choose where you do it. You're gonna get the same point anyway. It's just whatever is easier for me. So C is PAL. So this point right here is the same as C, which is negative PAL because it's simply the opposite of for this thing to be in a static condition. That's By. And then to find the maximum moment, it's going to be somewhere around here. So we have to use the force P. And then let's do that equation again. So we don't know exactly where it is we're going to solve for. So the distance is L minus X. X is whichever point on the beam from 0 to L. And that, remember, moment is distance times force. So that's the distance. And the force is the force that we already know. And the moment is positive. Okay. So that is the moment. So when L equals to L is 0, so it's 0 here and it's 0 here. Oh, sorry, when it's 0, it will be PAA. Yeah, correct. So that will be here. Let me check the values of the equation. When L is 0, we're going to have L minus X is minus X. So PA divided by L. We need to make this 1 to get the maximum. PA times L divided times L minus X. So this equation basically is, let me rewrite it. The force times the distance A divided by L, and then L minus X. So PAL is this slope, and L minus X is for this slope. And the maximum point where it's going to be when L, oh, okay, when L equals to, if L equals A, is L minus A. Divided by L, that multiplies PA. Okay, so it'll be PAL, that cancels out. And let me check with math, I need to get to this point too. Like writing it down is pretty easy. That's why I like to do the geometric figures, because you know that the higher point is this force right here, which we found with this. But with math, we also can find this if we didn't want to write it down, if we didn't have to draw it. So I'm going to just get some space and do this part again. Let me see if I have it solved here. So reactions and the diagram. Okay. And then moment. This is what we did before. All right. Yes, PB divided by L times X. That is this going up. And then the slope going down is here. The slope going down is right here. All right, PA divided by L, L minus X. If this distance is L, it'd be L minus L0. That is okay. If L is, if X is 0, it will be L minus 0L. So PA times L divided by L is PA. Okay, so this here is PA. So moment will be PA if if X equals 0. That's the moment at A, okay. And then the maximum be this point right here. PA, the maximum moment is P is AL A times A divided by L. A times B divided by L. Wait a second, why is that giving me, let me check something real quick. Very quickly. I need to make sure that I'm doing this part right. Um, the moment is there. L3 P half. So the moment here is PL divided by 4, which is the maximum. And the way you know that here. So mx0 at x equals, oh, perfect, L half. My bad, my bad. So when we do x, all right, cool. So when we do L divided by 2, oh no, or that's the issue. Okay. I was all this time thinking that this was at L divided by 2, but it's not. That's why I was not getting the answer. This point right here is at L minus B. So when you bring here in this equation, you plug in L minus B, you're gonna get that the maximum distance is, maximum moment is P, the force times AB divided by L. Okay, that's it. All you need to do is that equation right there. You plug in the distance at which the force is, and you'll get the answer. Cool. Yeah, I was getting worried that I was not getting the answer. Okay, let's do the other one. The other one is a little bit more challenging. So problem 2, we're gonna do an actual engineering problem. Where is my screenshot thing? All right, captured screen. Okay, so this is an engineering problem that is actually pretty interesting. So when they're designing the railroad, how come I'm not able to write on this? What happened? Okay, when they're designing their railroad, they have to put a base that is going to be supporting the beams, and then they put the actual rail, right? The I-shaped beam. So you have three components: the ground, the beam, and the rails. All right. So they're asking, what is the question here? The question is, the figure illustrates the car wheel supported by a railroad. Yep. And the wheels load acting on AB, so the whole load is distributed to AB. Assume that the reactions in the ground uniformly, so assume they are uniform. That's a good assumption. Determine the maximal values and bending moment. Okay. All right. So the first thing we have to do is to do the free body diagram. So as we said, we have a ground, the rail itself, and then the beams. So it's gonna look like so. It's gonna look like so, right? Like this. Okay. So if you notice, you have the 50 kilo PSI force on each rail, and then that's distributed on the beam, and then that's distributed on the whole ground. We're gonna call that little W for like reaction force. So let's optimize time here. I'm just gonna show you how it looks. So the forces on Y are W times the distance That's the whole force, right? So since it's distributed, we're doing the area. Remember, it's not moment, it's the area. This force is equivalent to all this area of 8 feet times the W. W is how the amplitude, right? Or omega, I guess, could be another way of writing this down. So omega times 8, because 5 plus 1.5 plus 1.5 is 8, minus, because of the way we're doing forces here, is down is positive, I mean negative. So 50, and we have two of them. So negative 2 times 50, that's equal to 0. Therefore, omega is 12.5 psi per foot. That is distributed load, right? That's the units of a distributed load, force by distance. So this whole thing, sometimes made of wood, mostly made of wood, um, is holding, each of them is holding 12,500 kilopounds of force per foot every time the wheel goes there, right? We're assuming at this point we don't care if the wagon is full or empty. This is the sensor is giving out this value. All right. So let's save this part right here. Actually, let's save the image too. And let's start solving it because they're asking us to draw the diagrams. All right. So from there, we're gonna start doing the sections. Remember, the whole point is to do sections. So let's do the first section. From A to C. So we're gonna, since we have a distributed load, we have to use a variable x because it depending, since it says that distributed load is gonna be a slope already or a curve. It's not gonna be a single point. It's not gonna be a line. We're drawing this as a slope or a curve. So that's why we need to do a continuous sweep. And AC, remember C is this point right here where the first load is, or 50 pounds per a point C as Charlie. So what that means is that if we cut there, we're gonna have a force of negative V and a positive force of 12.5 kilopounds per feet. Therefore, V is positive 12.5 kPa or foot times X, because it's really depending on the X. That's how we're gonna draw that force. So we already have a clue of our shear diagram having a slope from 0 to point C. If we do a moment at point J, which is a new point that we created in the middle between A and right after 50, so like right here or right underneath 5, whatever. It's a point in X that is right after the force C. Sorry, it's right before the force C. We don't have the force yet. So it's that point, if I were to draw it, it's like over here. It's between there and here, like somewhere around here. So we're gonna have it's going it's gonna be a moment at that place where we're cutting the beam, and it's gonna be positive because it's going clockwise. And then of course the reaction force is a negative x divided by 2 because we're replacing the force in the middle so that we can do the moment of 12.5 kPa per foot times x, which is the force V, right? So this is basically x divided by 2 times V. Well, what we're doing is placing V at the middle. That's a method that we already know, which is placing the force in the middle always. All right, we solve for that. We get that moment is 6.25 x squared. All right, so we already know that this is going to be some type of parabola. Cool. So we have the moment right before the force and right in the force and the V section right before the force to cut the shear force before the point C. So that's from A to C, right? That's right here. Then we do from C to D, which is in the middle. And from C to D is also interesting because now we're able to use the things that we already know from A to D. So we're gonna have a force, and now we cut again. All right. So between C and D, we do a cut, and we're gonna say that that force is 12.5 times X, because it's at some point, minus 50 by itself because it's a point load, minus V. Okay, V is always by itself. V is like a reaction here. You don't multiply V times X. If you solve for V as vector, you're gonna get 2.5 times X minus 50. Just solving this as regular math. The moment is interesting though because you have the moment that is positive at K, so M or plus M, minus 50. And what distance do you use? We're gonna use a distance of 1.x, obviously, because the x is the point that we're choosing, minus 1.5, right? So this distance right here, this variable distance right here, is x minus 1.5. Why? Because 1.5 is fixed, and x is the variable one. So if this was 3, it will be x minus 3. If this is 1, it will be x minus 1. If this didn't exist, it will be just x. Okay? So x minus 1.5 is this distance. So we're doing 50. So x 50 times x minus 1.5. That's right here because of the point load. Now, since we have a distributed load, we have to place it in the middle of that distributed load. So it's going to be 12.5 at x divided by 2. So like x divided by 2 will be like around here times the whole distance. All right. In this case is the whole distance because the force goes from A to D. 50 didn't go from A to D. That's why we had to do this number right here of x minus 1.5. If you solve for that, you're going to get that is 6.25x squared minus 50x plus 75. Okay? Don't worry, this is going to be this is going to be posted for you to revise. All right. So just like the homework, you start putting numbers for x and v. So v equals 0, that equals 4 feet. So if x equals 4 feet, you're going to get 0. And we're basically solving this. Let me just double check. Let me bring Wolfram alpha over here. Let me bring Wolfram alpha over here. Wolfram alpha. Okay, so we have well, we have a lot of variables though. So 6.25 times x squared, or any tool that you have to solve quadratic equations, plus 75 equals 0. X 25 x squared minus 50. Oh, this is, let me double check there's not a typo here. There we go. So at 2 and 6, we're going to use these numbers later. At 2 at 6. Okay, so let's get this right here. We're gonna save it for a minute. Let's save it here for a minute. We'll bring it back. Okay, so if in that equation right there, you say x equals 0, so sorry, x equals 4 times it's negative 25. Okay, so at x equals 4, oh, remember at this point, all we're doing is choosing some values to be able to get point to draw this. So 4 is right after 1.5, but less than 5, right? You can choose 3, like you can also choose 3. Oh my gosh, I'm not asking for m, I'm asking for 3. Okay, so at 3, you get negative 18.75. Okay, so you can get different values. You can use your calculator for this, obviously. All right, so we have that at 4, m is equal to 25 kilo psi per foot, or times foot, because it's a moment, right? Force times distance. Okay, so now we have for v. Oh, and what is x? We can just multiply. So 12.5 times 4 minus 50. Let's see. Let's see. We'll go back to Wolfram Alpha. And then we'll do 12.5 times x, which is 4, minus 50. Okay, and at that point is 0. So the reason why this one is a good point to choose is with v, the shear is 0, is because we can use that as a crossing point on the plot. You'll see in a minute. But again, if you also use 3, then you write that number down. So it's negative 12.5. So at 3, so right here, v is negative 12.5 kilo psi. All right. Obviously, you want to know the 0 for v and the 0 for m, so you can know how to write it. Like you have an idea of how to draw it. All right, now we have 2 points at 3 and 4. So when you draw this, it's going to look like so. This is going to look like, let's do the shear diagram first. The shear diagram first. The shear diagram is going to look like this. So this is the same image, and then he says that at 0 is going to be 0, obviously, and at B is going to be 0, obviously, because there's no more material. So all the forces are between A and B. Then it goes up. Remember we solved for it? Oh, we didn't solve for it yet. No, we didn't solve for it yet. Okay, so we're not ready. We're not ready to show this yet because we don't have all the information yet. Yes, we don't have all the information yet. Let's see. 12.75. Well, yeah, we do. We do have all the information because I thought we have. Oh, right here. We have it right here. I couldn't see it. I couldn't see it. We have it right here. Okay, so 12.5. Where's my Wolfram Alpha once again? All right, 12.5 times 1.5, 18.75. All right, cool. So that's why you have an x, right? That's why you solve in terms of x. Remember, this equation right here is for the distance from 0 to the point load. And if you since you're expressing it as in terms of x, then you know that this is the slope. And with that slope at 1.5, you get 18.75, which is exactly what we got right here, 18.75. All right. So 18.75, good. Then we have a 50 kilopascal force. So this one minus 50, it goes to negative 31.25. And That's exactly right. This whole thing will take you down to negative 31. Remember, this is a vertical axis with units kilopascals. Kilo, oh, sorry, not kilopascals. Oh my gosh. Kilopounds, kilopounds. We're in empirical system, not international. And pascals are force, are pressure, not force. It will be kilonewtons, not even pascals. So this is kilopounds. So kilopounds, 18.75 up, negative 31 as a point load, so it's vertical. And then this slope right here, which we already solved, um, we should have that equation somewhere here. I think should be underneath maybe. But let me bring it back up. That second equation is this one. Yeah, we did solve it from C to D. So that second equation is from C to D. It's 12.5. Remember, this is the first part of it, minus 50 minus V. And then we solve for it, it's 12.5 times X minus 50. So if you put, what is this distance? 5 plus 1.6.5. If you plug in 6.5, so it will take us to 12.5 times 6.5 minus 50, 31.25. All right, cool. So we'll go back there, then negative 50. So that negative 50 is 18.75, negative 18.75. Yep. And then back to 0. Okay, so that's our shear diagram. Let's go to our moment diagram. Our moment diagram. So what I want to do is I'm going to put all diagrams together. So I should be able to do it like so. So the diagram go first here. And now we're ready for a moment diagram. I'm gonna just share it and then we go point by point. All right, so remember, this is why it was important to plot the quadratic equation because we needed to know the points here and here, which is where it crosses 0. It's gonna start 0 because we don't have any reactions here. So since we don't have any reactions out of A and B, there's no moment there. Okay. And then we have that from, so we know we have certain points that are important. We have one right here, that is the center line. We have one right here. We have one right here. So with those points, we can draw our diagram. So again, we just have to use the equation that we had before. Where's my equation that I keep losing? So from A to C, from A to C, from A to C, we have 6.25 x squared. So let's do a point at 1.5, for instance. Like you can build a graph with multiple points, and you can actually put it in Excel or Python and do each point as a symbolic graph. So 6.25 times 1.5 times 1.5, which is 1.5 squared. 1406, right? Right here. That's good. Then we need the next equation, which is the one accounting for the 50 PS kilopounds. So the next equation is from C to D. That equation is right here. That equation is right here. So, and we already solved it. It's negative 25 kilopascals per foot. So that's right here. And since this is symmetric, this is the same thing right here, 14.06. So this is the moment diagram. Okay, pretty straightforward. And then what is the maximum? You just simply have to put that distance of 4 in your equation, and it will give you the maximum values for your shear and for your moment. And actually here, so you see the recording, you can practice. I just put in those values in the equation, and the maximum is 31.3. And we already know that the maximum is 25. Okay. How do you know that the maximum is 31.25 is the maximum? It's not located at the center, it's located at each beam, at each point, right? Here, D and C. All right, cool. So review this problem. All right, I'm gonna do one last one very quickly because we only have like 9 minutes. So let's do this one. And let's do, all right. Again, draw the shear and moment diagram for each. Draw the shear and moment diagram for this problem. What is going on? All right, so what you need to do is move this 120 to the beam. Each force needs to be moved to the beam. And you have to move through the material. You cannot move through air. This is not radio frequency. You have to use the material to move your force. So this, if you translate, if you want to move this force, the easiest way is to use moment. So this force right here, this 120 newtons at 200 millimeters back here, is the same as a moment right in the core, mathematically. The material might not behave the same, and you might have cracks over time that you learn that later. But in conceptually, for this to be statically correct, a force up here at this distance is the same as a moment right here. Later, choosing the materials is a different thing because a ceramic with this force will break right away. That's why we use aluminum and things like that. Okay, so since we're running out of time, I'll just give you the highlights here. So you're gonna have to translate the moment to the center. Remember, when you move a moment, you bring the force also to that point. So you need to keep the force, and it's just the force times the distance creates a moment. So by moving the force, you don't lose the force. You move the force to the center, to the point, and then you add the moment. Since this is doing a counterclockwise rotation on the part, on the element, it's going to be a positive moment. And 120 times 0.2 meters is 24 Newton meters. All right, this is free, so it's only AY. This is fixed, so AB and BX are 0. All right. So in order to create the diagrams, you need to solve for um, the forces. Okay, and the forces are solved like so. Remember, in X is 0 because you have only one force, so it is not going to move. It's in Y that is a problem. So you have A minus 120 minus 123 times, yeah, minus 123 times plus 120. Hold on a second. I think that there's a typo here because we have a force in By and we have 1, 2, 3. I think this is a typo here. I had a typo here. Okay, so did that change my math? It did. It did. Let me see. 3 times 120 is 360. Wait, did the prong give me an extra force that I don't know about? No. Okay, there's a typo. This 120 shouldn't be there. Yes, that's a typo. So 360, my apologies. So this is not right. It's 360. All right, the reason is that you have three forces coming down and one force holding that together. All right, the moment for it is this one. So obviously we want to get the moment at A, which is, or a B, really doesn't matter. It's whatever we feel more comfortable. So B, if we do it at A, By times 246.6 meters, negative 20 times 0.2, negative 20.04, negative 20 times 0.6. Oh yeah, if we do it here at A, we can cancel that force. So if you do it here, you can cancel this force and you can only use these two, 120 times 0.4 and 120 times 0.2. That will give you 120 newtons. That's By. And with that, you can create a method of sections. And if you go ahead and do that, you'll be able to see that if you do a cut right here, for instance, right there, you transfer this 120 here to point C, and you use the X variable again to be able to plot any point you want. You're gonna have the negative 40, negative 240 in X plus 24. Let me see, 24. This is the moment, right? Using A, so that will create a counterclockwise. Be careful with your signs. So this moment is counterclockwise. So you just place it there. It's 24. Then you have 120 x minus 0.2 because it's whatever point we want. So like from here to here is 0.2. Remember? So it's the same thing as before. X minus 0.2 is this distance. Or basically, sorry, this distance is 0.2. 0.2. This right here is x minus 0.2 times 120 plus m2, which is what we're trying to solve. And since I had a typo, I don't think this is going to be 240 anymore. Right? It's going to be 360. Yes, it's going to be 360. So negative 360. All right, so this is wrong, is whatever this new solution is. Okay. So if you plot the whole thing, we're gonna get this graph. So a 240, maybe actually a 360. Let me see. So it's 360 minus 2 minus 120. It's 360. Let me see the calculator. So 360 minus 120, 240. Okay. So minus 120. Oh, I see what's going on. Yes, yes, yes. Okay. This will By is By 0. Determine the maximum volume. Did we say that BY is 0? No. BY is 120. Oh my gosh. Yes, BY is 120. I completely made a huge mistake. So we're correct. Yes, we are good. We are good. It's not, this is BY. This is BY. So A and this is BY. And this is the three forces. 1, 2, 3, and then BY is 120. How do we know? It's because when we do the moment, when we did the moment, we needed to do the moment first because we had to one equation to unknown. So we always usually do the moment first. And it's BY times 0.6 minus 120.2, 122.4, and 120 times 0.6, which is 2.2 plus 0.2 plus 0.2. And then the three moments at 24. That's the part that we skipped. So when we do the moment at A, you get BY is 20, 120. And then the summation of force at Y, you get 120 plus A minus the three forces. A is 240. Yes, we're good. So that's it. That's, and then once we have that part, we can go back to do the other side of the beam. So let's, now that I'm convinced that that was correct, let's do this part again. All right, so once we cut again, we have that this is reaction at A, which is, we just solved it, 1, 2, is 240, right? This is the one that we solved. This is 240 times X. This is because we're doing the moment, plus 24 minus 1, 2, minus 120, X minus 2. We're ready this part. Okay, so solving, V2 is 120 and M2 is 120 times X. Cool. So we're gonna use this for the graph, 120 times X. Let's do this part like so. Let's save this part right here. I'm gonna save this part right here. All right, that's moment 2. And then for the last moment, we're gonna do this part right here. All right, there you go. So we have 0.6 minus X to get to BY. This is the variable distance right here. We have a moment of 24 Newton meters. It's 24. And the reason we have that moment is because if you remember correctly, the original geometry had this force of 120 here. So when you bring everything down, when you bring everything down to the beam, you're gonna have this force right here. You have this 24 right here. Okay, so in other words, you have M3, which is this moment, minus 24. So M3 is 24. That's all you have to worry about for that part. Okay. This 24 is from this force right here at point B. Okay, so now with all that, we're definitely back to a good spot to draw everything. All right, so once you have your beam and all the forces, you have that A, reaction AY is 240. So you have a straight line, then 120, one straight line down, at D, you have straight line down, and then at B. So the end of the problem is right here. So this is AY, straight of 340, 240 to 120, 120, and 0. Now we have the moment. This right here is, remember that we had it right here, I just erased it, but I have it here somewhere. So 120x. So this is 120x because since this distance is 0.2, so 120 times 0.2 is 24. 120 times 0.2 is 24. And 48. Let me see. So we started from where may not be. So 120 times 0.2 is 24. So we go straight up. So first of all, this is 24 right here. So let's draw it, 24 right there. Then we have another 24 right here, positive, right here. You draw it. So that's another point. Instead of drawing lines, I'm going to draw points. So we have a 24 right here that is given by moving the forces to the B. Another 24 right here, and another 24 right here. And we know that that 24 connects to 0. That's the first line. Okay. Now we know that this one is M2 at 120 times 0.2. So that 24, so 24 plus 120 times 0.2 is 48. There you go. So these 2 points connect. Yeah. And then the same thing is here from here to here. 120.2 is 48. And then there's another force right there. And then By is 120. I think should be like this. I think that should be like this. I think I made a mistake. So it's 240, 120, 120, and By was also 120. By was also 120 up. Yeah, so oh my God, GTS, that was definitely a mistake. So it's 360, 240, 120, 0. Should be like that. I apologize. Should be starting at 320 and going to 240 and going to 120 and then 0. Okay, and this one is like this, 48, 48, and 48. Okay. All right. If you have questions, let me know. We have a question here. Would that be yes? Thank you so much. All right, I'm gonna try to fix this a little bit to post the document with the flow so you can follow it, and then I'll post the video too. So if you have questions, let me know. All right, we're passed over, so I'm gonna finish here. Questions, concerns, comments?